Uh, Good afternoon. This is, of course, Comp 725, North Carolina A&T State University. So let's get started. All right, hopefully, yes, hopefully you can see the screen at this time.
Yes, we can.
Thank you. It's not always easy to tell what you can see. All right. And just to make sure you're good computer science students, anybody know who Grace Hopper was? Nobody? Well, Grace Hopper, Admiral Grace, yes?
Don't know much, but I think computer scientist,
Yes.
American computer scientist, right?
She was a pioneering computer scientist. She was an admiral in the Navy. She developed the COBOL language, which I understand, of course, COBOL is ancient and it's really a miserable language, but it was one of the first high-level languages. Previous to her, all programs were written in assembler, which is even worse. So she was a computer science pioneer. She gave a whole bunch of talks. I happened to have the opportunity to see a talk from her. She used to hand out pieces of wire that were 11 inches long. It was a nanosecond. She said, that's a nanosecond. If you want to make something faster than a nanosecond, it has to be smaller than that. Okay, well, moving on. A couple quick announcements. The course evaluations are available on the Blackboard system. You should honestly evaluate all of your courses here at A&T. There's a set of about 25 questions that you should answer. It's pretty quick, easy. Make sure that you do it. The evaluations are open until December 5th. So you've got a couple weeks yet, but I wouldn't wait. Right now, only about 17% of these students have completed the evaluation, which isn't a very representative sample. So please do it. Now, note, because my name is now connected with the course, if you are evaluating the course, you're evaluating me, so you can let me have it. Tell me what you think. If you do have comments for Dr. Yuan, put them in the free response question or answers at the bottom of the page, bottom of the exam, at the bottom of the survey. If you want to leave a comment for Dr. Yuan, I'll make sure she sees them. Okay. On Monday, November 29th, and that is 2 weeks from today, we have a senior manager of application security, Kristen Bell from GuidePoint Security will be lecturing us. She actually does what we talk about in this course. She is a computer security professional. She'll talk about the state of application security today and how everything has changed over the last 15 years or so. So you want to hear that? I think we'll have an opportunity to find out how this really is done. Now, she's going to be presenting via Zoom. So I suppose if people want to, we could, those who are part of the on-campus class could meet in McNair Hall and watch together, or we could just do it all via Zoom. Those of you who are normally part of the on-campus class can give me your opinion on that. My thoughts are leaning towards just doing it all online. So she's unavailable to come in. She has to do it via Zoom. So that's what we're going to do. So anyway, if you have an opinion one way or the other, and you are part of the normal on-campus portion of this course, let me know if you want to meet as a group on campus or whether we should all just do it via Zoom as we are doing today. All right. We are on Unit 12, and we're talking about overflow threats today, and part of the topic of how vulnerabilities get into all software. Well, it's all about you. How do they get in the software? You write them in. As a programmer, if you write insecure code, then you are putting the vulnerabilities in the software yourself. But of course, you're also the opportunity to fix them. If you code it correctly, if you are careful about the known vulnerabilities. If you take the steps to avoid those problems, well, then you'll help protect your users from attack. So here's a clicker question of which I happen to have a poll. So take a look at this. I'll have a Zoom poll in just a minute. You might want to take a look, though. It's easier to see this on Blackboard site. Okay, on Zoom. All right. So we're looking at this C++ program. Of course, take note of the 4 and the 7. And so please answer that question. About half of you have answered so far. Oh, there's some more. Okay, people, answers are coming in. One more person. Think they have to wake up. Oh, they may have fallen asleep. So we'll let it go. Well, here are the results that you can see. Let me just see if I don't know how much this you see, but yes, 7 out of 8, 88% of you said there would be a runtime buffer overflow error. And one person thought the compiler would catch it. I'm sad to report that none of the above are true, that in fact, the compiler will not catch it. The runtime system will not catch this on a C++ program. This will simply corrupt the data and cause strange and unusual things to happen in your program. No, this is a C++ program. Had you written it in Java, Java would have caught the error, but no, C++ does nothing to stop this. Here's an example of the problem. Imagine we have the program here where we have a Boolean, which I'll call root privilege, and we'll set it equal to false. And we'll just, for the sake of making it interesting, of course, assume that if root privilege is true, then you're an administrator and you have root privilege. And we're asking the user for their name into a character string of 8 characters. Of course, in C or C++, or at least C does not have strings. We'll talk about that. There's an array of characters, and you use the cin to read into the name. And of course, the user types in the name Smith. Then you can see in the graphic here that the characters SMITH, on the 6th character, there will be a 0, a null character, because strings are terminated by a null character in C. Now, what if the person's name is Armstrong? Well, that's 9 characters long. And so it'll put the first 8 characters into the character array, but the 9th character will go into the next memory location, which in this case is the Boolean variable root priv. So that variable will be set to a G. Of course, it is a Boolean value. In the C or in C++ language, a Boolean value, again, can be Boolean or ints or any almost any type, is true if the value is 1 or any, if it's anything but 0. It's false if it's 0, true if it's anything but 0. So this will set root privilege to true. Here's a more complete example of the program, which I actually ran, and I'll show you the outcome of that. Here we have an integer value that represents the root privilege, and you set it equal to false. We then have a character string that I put some letters in there just to make it easy to find in the memory. And then, of course, there's the rest of it goes to, ask the user to enter their name, read it in. And then I print it out. I also print out the root privilege variable or not. Okay, so that's the program, pretty simple. I ran it with the debugger. That's when I ran it with the debugger, I stopped it at the C out, and I stopped it later on before it actually prints the result. Okay, so I used the debugger. I turned off some of the protections that Microsoft Visual Studio puts in there. We'll talk about those in a minute. And I also turned on the option to get an assembler listing or a listing of the assembler code generated by the compiler. This is useful to find the location of the variables in memory. And then when I stopped it, I asked the debugger to show me the value in the extended base pointer register, or EBP. The EBP points to the beginning of the stack frame in memory. This is not a programming languages or a hardware class or anything, so we won't really go into the details, but just say that the base pointer register points to the stack frame or where the local variables of this method start. And here is what I see in Microsoft Visual Studio when I asked to look at the memory. Again, I got the address of the base pointer register, and I could find the array name. And if you look on the right, you can see it goes A, B, C, D, and then E, F on the next line. It wraps around. So name is 8 characters, the first 4, which are A, B, C, D, and then the E, F, and a null character, another null character here. The variable root priv is right after it in memory. If you notice memory addresses, if you look on the left, go down. So this is a smaller address at the top and a higher address at the bottom, if that makes any sense at all. Okay, and so you can see root priv is 0, being false. And then this is before the input. After the input, the Armstrong is entered. You can see the variables AR, you can see over here where it displays it in text form. Here it displays it in hexadecimal. The A, because I had initially had A, B, C, D, and then typed in Armstrong, the A didn't change. It highlights what characters were changed. And you'll notice, of course, that 67, the G, appears in the root privilege variable, which previously was all 0 and now is a non-zero variable. And so now, because root priv is non-zero, it thinks of it as being true in the logical sense of the C++ language, and therefore we've changed the value of root priv, even though the program itself does nothing to change the value of root priv here. It simply changes the name. So that's a buffer overflow. A variation of buffer overflow is stack overflow, particularly useful or dangerous, I guess, if these are local variables that you are changing. Remind you of how memory is allocated, that local variables are on a stack. As you call methods, you get a new stack entry pushed on top of the stack. And so you have the data on the stack along with other things such as the return address every time you call a method. Well, here, let's take a look in detail at this. Okay, first of all, stack overflows are the big threat. They may not be what happens most often, but when they occur, they are probably the most dangerous of all vulnerabilities. Every now and again, you'll be reading a description of a problem. Microsoft sends these things out every now and again, and you might see the phrase, the most severe of these vulnerabilities allows a remote attacker to execute arbitrary code. When you see that, it's almost always a stack overflow. Interesting historical note, for those of us who are old and gray, the Morris worm, which was the first internet worm, was spread in part by stack buffer overflow in the finger application on Unix. Unix has a finger asks for information about a user. You could ask who they are, and it'll give you information. There was a vulnerability in that application and over. The internet worm, Morris worm, was pretty effective. It pretty much brought down the internet for a day or two, attacked a large number of machines on the internet at that time. It was, oh, I can't remember when it was in the 80s. It was generated by a student. The student claims it was sort of an accident. He built it as a demonstration and it got loose. He was only going to run it in his lab, but it got away from him and attacked almost everything on the internet. Yes, he was caught, and he had a fine. He had a pretty significant fine because it did cause a lot of trouble. Okay. Now, there is another thing you call stack overflow. People refer to stack overflow when the stack gets too large and expands beyond the available memory. That happens if you have great big arrays on the stack, or if you have runaway recursion where you're just generating more and more stack entries. That's usually not a security issue. That's usually caused by some programming problem, and we're not going to talk about that today. We're going to talk about putting variables on the stack and how this can generate a vulnerability. Let's talk about how information is pushed on the stack in some detail here. All right, here's your memory layout, your logical memory layout. Now, of course, if you have a machine with virtual memory, your memory is broken into little pieces and scattered all over throughout the machine. But this is how it logically looks. Here are the different program segments that you have. You have your program instructions, that's the machine language that you're executing. Then you have some global data and constants. Then you have the stack and the heap. The heap is where your program allocates memory for dynamically acquired thing. If you create a new object, if you go new and you create something new in the program, it is the memory for that is from the heap. The stack is where it puts local variables and method call information. And we'll talk about the stack. I might note that in the Intel method, the heap and stack kind of start at some arbitrary large address, some large number, and then the heap grows to higher numbers, to higher addresses, and the stack grows to lower addresses. The stack will grow into lower and lower addresses until it runs into the global data, at which point you have the stack overflow that's generally not a security problem, and you run out of space, and errors occur or strange things occur. That's not the stack overflow we're going to worry about. Here's an example. Okay, we've got a simple function that takes the address of a double and an integer value. And the method has a local variable called cow that's 4 bytes long. And then we will call it from the main program, and we'll just pass it an integer, a double. Trout is a pointer to the double, so we'll pass it with that pointer to the double and the integer value. So this is what the stack will look like. The first thing the software does when you're calling a method. Now, again, this happens, all the code is created by your compiler. When you call a method, it does all this for you. And I might note that calling a method generates an awful lot of code behind it. Those method calls are not cheap. While good programming standards require the calling of methods, there's a lot involved in calling a method, including a lot of code that's generated by each method call. So the first thing this compiler will generate is a call that will take the value of the BAS variable, which we'll just say was 5, and push it on the stack. So there on the top of the stack is the value of BAS. That BAS was the variable it pushed. Then it pushes trout. Now again, trout was an address to a double. So we have the address of carp. Carp was what we're passing back. Trout. So that's the address of carp, which is the variable trout. So it pushes the address there. Okay. Now we do the method call. We push the parameters on there. The method call pushes the return address onto the stack. So the next thing about top of the stack is return address. We refer to this as the top of the stack. Our little arrow here on the right points to the top of the stack, and the top goes down. I know that's like opposite of what you probably heard in your data structures class, but again, the Intel system and several other systems push things on the top of the stack and lower addresses. Okay, so we now have the return address on the stack. The next thing, we push the frame pointer, which points to has the address of the previous frame, which we'll not go into in this class, but it links all of these areas in memory for each method call are all linked together. This is particularly useful if you get an error and it shows you a trace of the stack call, what's on the stack, and you get an error called this method, called this method, called this method. That is found by tracing back through these addresses from frame to frame. And then we allocate space for local variables. In the case of this program, we had a 4-byte value, which is an array of characters. I called cow, so there's cow on the local. So there, that's what it looks like as the memory locations when we have the local variables, the return address, frame address, and then the parameters. Now, as these are pushed into lower and lower addresses, as you put data into, if you get higher and higher addresses, it goes up. This is low, down at the bottom, cow is at the address that has the smallest numerical value, and bass is in the part of the stack that has the highest numerical address. The problem is that if you go past the end of cow, you start going up into the frame pointer, the return address, and the parameters. So in particular, say that cow 0, 1, 2, and 3 are in the cow variable, but cow 8, 9, 10, and 11 are where the return address is. So if a attacker can craft the appropriate input, and it's not checked by the program, that if they can change cows 8, 9, 10, and 11 and put a value in there, they can change the return address. So when the method returns, at the end of the method, when it goes to go back to the calling program, it will go to someplace else or crash. So they have to be careful about that. Yes, again, if you have a short buffer and you put a lot of it, you can put additional for it. In addition to changing the return address, they can also load binary machine language into the rest of the stack. If you have a short buffer, if the user expects a short answer, say they ask you, yes or no, and so they've allocated 4 bytes to hold a yes or a no. No is only 2 bytes. Yes is 3. 1 more byte for the null character at the end. And so they have a 4-byte, which would think would be sufficiently large. But the attacker doesn't just put that. The attacker puts a very long input, long enough that not only changes the return address, but loads machine language, the assembled or compiled version of a program, onto the stack of this program. So it overwrites the return address, so it will jump into the code of the program that was loaded. You can also change the return address to jump in someplace else in the program that already exists. And you can even, not only can you push the return address, but you can change the parameters as you wish. So you can change the parameters and call an existing method. So here's another clicker question for you. What is the most evil thing a Stack Overflow exploit can do? Let's look at that on the poll question. So there you go. Think about that. We had one answer, and I think it was a good one. Okay, anybody else want to put their opinion out there? Okay, we've got 8. Oh, everybody's there. All right. So there are the results. As you can see, 44% of you thought changing the return address to call some function was dangerous. And that is, of course, particularly dangerous. 11% thought crashing the program was bad, and 11% also thought altering data was bad. But in my opinion, in my experience, loading binary machine language is the most treacherous, evil thing that you can do with a buffer overflow exploit. The reason being is that if they load binary machine language onto the stack, they're loading their own program. In other words, they're loading their program onto your computer and executing it on your computer. So now their program, which you know nothing about, and is probably not going to do anything friendly, is running on your computer with all the privileges that you might have. And if you happen to be an administrator, you're in big trouble because it can do whatever it wants. Typically, in a real attack, the first thing that program that loaded does is go load a larger program from someplace on the web onto your computer and start running it. And then you're in real trouble. Okay, so if you're an attacker, how can you tell if a program is vulnerable for buffer overflows? Well, the key is generally putting in very large inputs into all the input fields and seeing if it does anything. Does the program behave differently? If it asks for yes or no and you give it yes or no, it does this. What if you gave it a big long input? Does it do something different, or implying that maybe the program crashed? Yes, a website here from Guidance Share talks about how to test for buffer overflows, and I got some information from them. They recommend, if you're trying to attack a buffer overflow situation, that some of the really good data put in, particularly if the information you're entering is going to be used to calculate an internal buffer size, well, try giving them a 0 or a -1. Do they check to see if the numbers are negative or nothing? And then give them the maximum size allowed by the data type. If you're doing an int, that's usually 4 bytes, or give them the minimum size. Particularly if you're handling large values, give them the max int or min int. Also, of course, if the size is tied to the size of a buffer, give them the size of the buffer +1. Do they check for that edge condition, or the size of the buffer -1 to see what happens? Other particularly nasty inputs is get a whole bunch of the character A's. A is just just one character. It's easy to put a particular character. Give them a whole 10,000 of them, 10,000. Just create a file with 10,000 A's. It's not hard to do. You can just sit there, hold the keyboard down, get 100 of them, then copy and paste. I didn't put this in the question, but how many copy and paste actions does it take to create 10,000 if you typed in 100 yourself? Well,
wouldn't it be easier if we just write a for loop that prints 100 times A?
No, it wouldn't be easier, because if you just got your notepad and you hold the A character down, you print out 100 until there's 100 of them. Then you copy the whole 100 and paste it. Then you copy the whole thing, the 200, and paste it. And you copy the whole 400 and paste it. After 7 of these, 10 of these paste operations, you now have 10,000. Log base 2 of 1,000 would be 10. So I think I can do that faster than writing a program with a for loop. So you create, whatever you do, though, or you can go out to someplace and find a text in some website, just copy all the text and then put it in there and see what it does. That would be good for a random string of size. One of them is do constant characters with no blanks in them, by the way. Don't put blanks. A constant string of non-blank characters, because something will try to split them between the blanks. And so don't give them a blank, give them a long 10,000 characters. Another thing, if it's expecting a URL, a link address, you give them the site name, and then slash, and then a really, really long string. And you might end it in .html after you put in 10,000 characters. Again, no spaces, lots of random characters. And that should, it's possible that they didn't expect a 10,000 character link and they don't have memory reserved for it. And that will, of course, cause the buffer overflow. All right, that's how you might cause them. How do you fix it? How do you prevent your program from doing that? Well, better software engineering. We talked a little bit about that last week, but you need to write your programs carefully and design them with security in mind from the very beginning. There are several other things here. I'm going to go over each one of these in more detail. First, the proper choice of language. C and C++ are particularly vulnerable to buffer overflow. Java, PHP, and the .NET languages like C# are not vulnerable. You might note that PHP is an interpreted language. The .NET languages in Java run in a virtual machine, that all of which check every array reference and make sure that you're not referencing outside the limits of the array. So in Java, you just don't get a buffer overflow, because as soon as you try to put a variable or a value into an array past the end of the array, you'll get a array index out of bounds exception, and your program will stop. Now, of course, that does cause your program to fail, but it doesn't allow the attacker to put arbitrary code in the stack. Another way to prevent this from happening is having the compiler put what's called a stack canary between memory values. A stack canary is basically a random or sometimes a constant value that's placed between them. So in the example here, after the variable cow, which is 4 bytes, we put a stack canary value. The stack canary value is placed there by the compiler, so it takes up more memory. So there's, in a sense, adds an extra memory location for every variable. So if you have all simple variables, it doubles the amount of memory. Although if you have an array, it only puts one at the end of the array. And so if the program gets too large, say if you go to cal bracket 4, cal bracket 5, you'll be changing the stack canary. And so before doing the return, when the method is supposed to return, the exit code generated by the compiler will check the stack canary values and see if they're set to the value that was stored. If they are set to that value, then it's okay. But if they've been changed, it knows that something's happened on the stack has been corrupted, and typically the program stops. Now, of course, the attacker has crashed your program, but they didn't get the opportunity to run arbitrary code in the machine. Now, stack canaries can be defeated. It's not all that hard. I've done it myself. Because if you put the right value where the stack canary goes, the compiler won't know. In Microsoft Visual Studio, it uses a constant. The constant is the hexadecimal value of all C's, C being 12 or something. So all the C or CC bytes in ASCII or Unicode, the CC character looks like this kind of graphic here. Those of us who are old and gray remember before they had Windows system, people would generate what looked like a window using the proper graphic or characters on the screen. So this is a corner of a box. But anyway, this silly character will appear, and they put that. So if you overwrite the stack canary with this value, at the end of the method, when it goes to return, it will check to see, is the stack canary kept set to CCCCCC? And of course, it will be if you set it to that value, and therefore it won't know that you've done a stack overflow. So the canaries are very good against arbitrary, accidental overflow or naive attacks, but a sophisticated attacker can put values in there and get past the stack canary. The hardware on most modern processors have a feature called data execution prevention. It's a bit in the page table. And if the bit is set, then the machine will not execute instructions from that page. In other words, when it goes to do an instruction fetch, if that bit is set, you'll get an error, and it will typically stop your program. This, of course, is a hardware feature. It's on the Intel processors and the AMD processors. I don't know about ARM, but probably ARM. And again, while your program could still load code on the stack, when it goes to jump into the stack, typically the stack will be marked as no execute. You cannot execute instructions from the stack, because a normal running program executes instructions only from the program segment. It does not execute instructions from the heap, the stack, or the global variable area. So if you try to execute instruction from those segments, then you'll get a data execution prevention exception and your program will stop. So that's a hardware feature that helps prevent, well, it does prevent writing, or it doesn't prevent writing the data or instructions to the stack, but it prevents you from executing them. Another feature that Microsoft Windows implemented a few iterations ago is random stack location. In other words, the stack in your program doesn't always start at the same address. Previous to this, it always started in the same place. And every time you ran your program, values in the stack would always be in the same location. Pointers would always have the same value every time you ran the program, unless, of course, you modified the program. But once you created it, when you ran it, they'd all be the same because they pointed to a location in memory and would always load your data into the same memory address. Well, they added a feature that randomizes that. In Microsoft Visual Studio, you can turn that feature on and off. By default, it is on. So every time you run your program, the memory variables are in different locations. This is an advantage to protect against attacking because otherwise, an attacker can sometimes run the program, figure out where the memory locations are, where your program data is, and then when it runs it again, it knows the addresses. So it can put addresses in the overflow data. But if it randomizes the address, then it's very hard to find things. There are multiple tools that will read the source code of your programs and look for various stack and many other threats. I went out and got a list of them. Here's 5 programs or programs that check your program. They read that. And it gives information here. Most do either stack analysis or flow sensitive analysis. Flow sensitive analysis means it virtually executes it and goes through and watches as it executes. Static analysis means it just looks at the code as it was written and trying to find problems. Interprocedural means it looks at multiple methods and doesn't just look at one particular method in itself. I noticed just now that all of them, oh no, some of them are intraprocedural, meaning it just looks at one procedure at a time or one method at a time, whereas interprocedural looks at the methods as they are called. Okay, anyway, but there are tools, and you can download these tools. I believe they're all available for free, and you can download these and run them against your program and see if they identify any problems. And there are more than this. There are many other tools that you can run to help identify things. And several of the compilers now have features that will help try to identify potential problems. A lot of the problems in the C and C+ language come from the fact that the original C language, written way back in the beginning of the 70s, did not have a string data type. Original C was pretty primitive. Of course, that was 50 years ago, and it was not an object-oriented language. It did not have anything but your basic primitive types. It had characters, and you could have an array of characters. Array was about the only built-in data type. And so if you wanted to represent a string of characters in C, you had an array of array of character values. The end of the string was denoted by a null character, 0, or backslash is 0 if you're writing it. And so that means there has to be one more character in the buffer than the number of actually printable or visible characters that you see. And if a program wants to find those characters, you have to look for them. In other words, it has to look down the string of characters looking for a 0. It also means that programmers cannot have a 0 in them. In other words, a character array cannot contain anything. It was the programmer's responsibility to make sure that there was enough space, that not the compiler or any of the methods automatically checked to see that there was a sufficient space. And of course, in programming, the off by 1 error occurs more than you'd like to think. off by one, particularly current arrays, is people forget how long the array is. Remember, if you have an array of 10 variables, they're indexed 0 through 9, and an index of 10 causes an error. If you have Java or Python or PHP, then you'll get an array index out of bounds exception. Somebody asked Python. Yes, I thought I had put Python on the list. Yes, Python checks for buffer overflow exceptions. So Python is safe in that sense. But C is not. And C++, which is just C with object-oriented stuff tacked on, is not safe from that. And off by one errors, of course, occur when people forget to start by 0. There are also unsafe libraries. That is, there are a whole bunch of libraries that were made, 50 years ago to do string functions, to copy and concatenate and things with strings. And again, because they were written way back when, where people didn't have any ability to have a method that checked how long the variables. For instance, if you code in the Java language, Java knows how long a string is. A string is an object, and there are methods to view a string. And so it always knows how long it is, and you don't overflow. But in C, you don't know how long the string is. It's just an array. There's no indication of what it is. It's just a pointer. You pass a pointer to the method, and the pointer points to any memory location, which may be an array of characters or maybe a double or anything. It doesn't care. It has no feature to check that. So it just uses whatever it gets as a pointer. Here's a list of some, but certainly not all, of some of the dangerous functions that you might use in C or C++. Many of them have a safer version. For instance, getS. getS reads from a string. Also, the cin arrow feature reads into a variable without any concern about how long the receiving buffer is. It just reads as long as the user types input, it keeps coming in. The fgetS specifies the length of the receiving field, and it won't exceed the maximum length that you specify. Same thing with copy. They notice they have an N in the middle. That's strn copy, strn cat. Copy and cat and str and printf have N, the N meaning specify the size of the receiving buffer. I might point out that actually string cat does not specify the size of the receiving buffer. It specifies the number of characters that you can copy, the maximum number of characters you can copy. So if you have a string of 10 and you've copied 6 characters into it and you want to copy more, the maximum is 3. But if your program naively says, oh, this thing will hold 10 characters and you put 10 there, you're in trouble. It's going to overwrite that. And that's happened more than once. So that's still, still a problem. And of course, in all of these, it requires the programmer to accurately know how big the receiving field is. You have to specify the size of the receiving field, which is a programmer responsibility. It does not happen automatically by the compiler as it does in many other languages like Python, Java, .NET. The program has to, and they have to do it, of course, correctly. Using the size of feature in C or C++ is very helpful. You can go size of space variable, and it returns the number of bytes of that variable, which you can use. All right, that's stack and buffer overflow and some of the errors you can get there. I wanted to talk about integer overflow. Integer overflow is a separate kind of problem. Okay, and quickly go over integer numbers, or if you took the architecture class, then you know all this. But just to review, ints, regular old integers, or longs, or shorts, are all stored as binary numbers. Remember, of course, as you type things in, you type them in as characters, and then the system converts the characters to a binary value, which is stored in your int. Most machines use 2's complement. 2's complement is a means of storing negative numbers. Everybody stores positive numbers as just regular old binary, but 2's complement is a way of storing a negative number. There's also something called 1's complement, but I don't know if any machines around today use anything but 2's complement. But 2's complement, it's pretty easy to convert between a positive and negative number. If you want to change the value from positive to negative or from negative to positive, works same way. You flip all the bits. So you make every one a 0, every 0 into a 1. You do that for every bit, and then you add 1 to the number, add 1 to the result, and that will give you a negative number. Here's all the possible numbers for a 3-bit value. And 2 to the 3 is 8. There are 8 values. There's 0, which is represented by all 3 0 bits, 1, 2, 3. But then 1, 0, 0 represents -4, and you can see that 1, 1, 1 is a -1. So here's some examples of how to convert a number into 2's complement negative numbers. Say you have the number -3, and you want to get the binary value for it. So 0011 is the positive value for 3 in a 4-bit number. Then you flip all the bits. So 0's become 1's, 1's become 0, and you have 1100. Then you add 1 to the result. It becomes 1101, and that represents a -3. Okay, so let's say you have the number 1010 in decimal. What you want to know what that value is. Well, because the leftmost bit, the most significant bit in the 4-bit value, these are, of course, 4 bits, just for example. Most numbers are 32 bits, but it's kind of clumsy to show those. So the leftmost bit is a 1, meaning the number is negative. So we know this is negative, so we want to figure out what is it. So we flip all the bits. So the 1's become 0's, 0's become 1. So you flip that, you get 101. You add 1, of course, 1 plus 1 is 0. Carry the 1, 0 and 1 is 1. So you get 1100, which in decimal 1100 is a 6, but this is -6 because we started with the negative value. So let's give this a try. See if you remember your architecture. What's the decimal value for a 1001? And the poll is now open. Okay, anybody else want to throw in a guess? Well, you're lucky this is my architecture class. There are the results. The answer, which was found by 2 students, is -7. Do I have a solution here? No, I don't. But if you take 1001 and you flip all the bits, you get 0110. And then if you add 1 to 0110, you get 0111. And 111 is a 7. So the result is a -7. The answer E, -7. Okay. Okay. So still talking about 2's complement for a couple minutes, and we'll demonstrate why this can generate an error. So here's using addition. Say you want to add numbers. So we have the number 104, and we're going to add the number -16, which my calculator tells me we get the answer of, shouldn't get 98, should get 88. That should be 88, but yeah, it's correct. So you add them up, and of course this is a negative number, but you can add them positive, negative numbers works just fine. You can see over here on the right, 7 plus 2, and you get 9. If you get 104 plus a negative 16, you get 88. Not 98, 88. But this is, trust me, this is, in fact, convert this to binary, it becomes 88. And you just add up. So you just add them, and the fact that it's a 1. And you'll notice here that at the end, you get a 1, a 0 is a 1, 0 and a 1 is a 1. A 1 and a 1 is a 2, or a 0, 1. Carry the 1. 1, 1, 1 is a 3, which is 1. Carry the 1. The 1 and the 1 is a 0. And then the overflow carrying out of the sign bit is ignored. So the answer is a positive number. So we, the large number, added a negative number, and we got a positive number, like you'd expect in arithmetic. Okay. Now, let's try this example. We take the number 6 in binary, which is 0, 1, 1, 0, positive. Sign bit is shown in blue. And we add the positive number 3, which is 0, 0, 1, 1. And you add it up, and again, 0, 1 is a 1. 1 to 1 is a 2, is 0, carry the 1. That carried 1 and 1 is 2, 0, carry the 1, 1 and 0 is 1. So the answer is 1, 0, 0, 1, which is a negative 7. The answer to the problem a little bit before. But negative 7 is a negative number. You added 3 and 6, and I can do that without a calculator. You're supposed to get the answer 9, but in fact, you get a negative 7 because we're only using 4-bit 2's complement numbers, and the maximum value we can hold is 7. And so it's overflowed. We add positive numbers together, and we ended up with a negative number as the result. That is the vulnerability that we're talking about today. Now, here are the maximum ranges for 1 byte, 2 byte, 4 byte, and 8 byte values. 1 bytes go from, of course, negative 128 to 127. Shorts, you can see, I wouldn't bother memorizing this number. I just remember it's about 2.14 billion. Actually, probably I should remember it's 2.15 billion, but it's about 2.14 billion is all you can fit into an int. A number bigger than that will not fit in an integer. Now, long, as you can see, is a pretty darn big number, and for most things that you're going to do, you won't overflow that. It should be noted that in modern computers today, you can count up from 0 and in a not unreasonable amount of time, get a number that's bigger than 2.14 billion. You have to wait maybe for a minute or two, but you can count up and do that. I think you have to wait for a very, very long time to do that. So here's a question. I don't have a clicker question for this, but just think about this for a minute. Take a look at this question. Okay, well, it's pretty simple. This is not a Java class. Here's a pretty simple solution. We want cal plus 5 is less than 12. And that will do it. Here we have cal plus 5 is less than 12. Hey, pretty simple. You pass comp 163. Another way, of course, when you do a little algebra, you go back, you subtract 5 from both sides, and you end up with cal is less than 7. They are both mathematically equivalent. But if you did cal plus 5 and the user entered the value that is the maximum maximum integer value, then the processor would add the two numbers. It says here Java would add, but Java, C++, any language adds the two values. And you can see here in binary, this is the maximum integer value in binary. It's all ones with a leading 0. It's a positive number, but every other bit is 1. And then we want to add 5, as is shown here. Well, you do it, everything overflows. We ended up with a negative number, a very large negative number, by the way. But this is a negative number. What that means is if cal had the value of this very large maximum integer value, and cal plus 5 is a very large negative number. In that case, the if cal plus 5 is less than 12 would be true, because when it added the two values, it gets a large negative number. And of course, the negative number is less than 12. And so that would be true. whereas, whoops, excuse me, I'm sorry, cow is less than 7 would be false, because cow would be the very large number, 21, 2.14 billion. And that is, of course, much larger than 7. So if the program does arithmetic on a very large number, it can get incorrect results. And an attacker can enter very large numbers or carefully constructed numbers and get it to overflow. Obviously, if your program was designed to do a check, say, you're going to enter value count, but you're going to make sure that that value isn't too large, then you just do the count plus 5. It's not going to check. The check would be defeated. You want to do the algebra and do it correctly. So to keep things short, you want to check the value of numbers before you do any arithmetic with them. Don't do any add, subtract, multiply, or divide with the number, with a large number, until you've tested to make sure it's within the desired range. If it's not in the desired range, then you have an error, possibly an attack. Another thing you can do is use longs if you think the value might exceed the size of an int. Of course, you can still overflow along with a very large number, but if the attacker expecting an int, you read along, you can read it in and check then to see if it's too big. Long is usually an 8-byte value, and ints are usually a 4-byte value. In many languages, that's how it runs. Ints are 4 bytes, longs are 8 bytes. I might point out the C standard says, does not say how big an int is, does not say how big a long is. It just says a long cannot be shorter than an int. An int cannot be shorter than a short. So a short, an int, and a long could all be the same size and meet the C++ standard. But typically, most machines, ints are 4 bytes and longs are 8 bytes. All right, that's enough for today. A couple reminders. On 2 weeks from today, November 29th, we have a guest speaker from GuidePoint Security. Christian Bell, the Senior Manager Application Security at GuidePoint, will be talking to us. She said her talk should be about the state of application security and how everything has evolved over the last 15 years or so. It would be nice to have somebody talk to you who actually does this secure software testing as a profession, somebody who does this day in, day out, and learn what they do and what security threats they perceive. I have a question now from the students who normally attend on campus. Since Ms. Bell will be attending the class via Zoom, do you want to attend yourself via Zoom? Or did you want to come into McNair Hall and we'll all sit there and watch it on the screen and talk about it that way? Any opinions?
Zoom lecture sounds fine to me. Like
Okay.
attending via Zoom directly from our PC.
Okay, well, yes, we're Zooming now. I guess we'll, on Monday, 7 days from now, we will be, if you are in the regular on-campus class, we'll be meeting on campus in McNair Hall. Of course, if you're a part of the all Zoom, all online portion of the class, you don't care, it's going to be online like it always is. All right, but just let you know, in that case, 2 weeks from today will be online only. If you have an issue or problem, please send me an email and tell me about it. Otherwise, because Ms. Bell is going to be online, she can't come into campus. I don't know where she is in this world. She may be in Greensboro, but might not. So we'll be doing it via Zoom, and the class will only be Zoom. There'll be no on-campus class 2 weeks from today. But 1 week from today, yes, there will be an on-campus class. I remind you that course evaluations are coming up. They should be a link in your Blackboard. I know several of you have seen it. I don't know how anybody has completed the evaluations, but the evaluation system does tell me how many people have completed. I now know that only about 17% of the class has completed the evaluation so far. So please fill it out. You should do this for all your classes. The evaluations are very important. Long ago, I used to be the department chair. Before Dr. Yuan was the chair, was Dr. Dozier. Before Dr. Dozier, I was the department chair. And the department chair doesn't really know much about how classes are being taught. I mean, how does anybody know how I'm teaching this class? The only real way they know is from the student evaluations. I can tell you, as the being a department chair in the past, the administration takes a lot of consideration in the course evaluations. They really care about those. So please fill them out honestly for all your classes. Because right now, with only 17%, that is not a significant sample of the students. Unfortunately, while the administration is very concerned about the evaluations, they're not very good at statistics. And they sometimes think, oh, 17%, look at how they voted. Well, it's not a real good sample. If you were doing real sampling, you'd know that that's insufficient number of students to get an accurate measure, but they don't think about that. Some of them do. Some of them are old engineers, but anyway, do go out. I remind you that you're evaluating me, not Dr. Yuan, because at this time, my name is attached to the class, and so you're evaluating how I taught the class. Some of the questions are hard to answer that way, like, did you get the syllabus in the beginning of the semester? I don't know, I hope you did. I know it's out there on Blackboard. In that case, apply, answer as you saw it. Leave comments for Dr. Yuan at the end of the survey, if you would. But the last question of the survey is open-ended. Do you have any comments? Fill that in if you have anything to say to Dr. Yuan. Or you can send her an email or whatever you want. Okay, that's it for today. We will again be Zoom only on Wednesday, 2 days from now. And we'll be talking about social engineering. So I will talk to you then. Thank you very much.
All right. Thank you very much,
Okay.
Dr. Williams.
Okay, stop sharing. All right.
All right. Thank you very much.